Hello viewer, my name is Prasanjit. On behalf of all the co-authors Paul, Nick, Korak, I welcome you to explore the poster on covariation of long-term trends in surface water temperature and bio-optical indicators across the Great Lakes. This work is an extension of a trend detection approach that was presented last year October at the 2023 GRIS meeting for global and regional oceans, available on the GRIS YouTube channel. The approach combined spectral analysis and time series decomposition methods. In this work, we extended to more parameters and inland waters, and also explored the seasonality aspect a little bit more. The results are preliminary, and I expect to better explain this in a few months, but the presentation will provide you with an idea about where it's heading. This is our study area, the Great Lakes, which is Earth's largest inland freshwater system and comprises 5 lakes, as all of you know. The map shows bathymetry and hydrology of the Great Lakes. Bathymetry from NOAA NCEI, river data from hydrosets, watershed from USGS, and the elevation is from the University of Tokyo. The Lake Superior is the deepest Great Lake with an average depth of 150 meters. There has been minimal agricultural activity within the Lake Superior watershed, but mining is commonplace. Lake Huron has the longest shoreline of nearly 6,000 kilometers. The eastern part of the Lake Huron, Georgian Bay, is separated from the rest of the lake by a peninsula and island. Lake Ontario is the most densely populated with 9 million inhabitants along its western shore, so lots of human activity. Waters from the other 4 lakes flow through Lake Ontario to the St. Lawrence River, connecting finally to the Atlantic. Lake Erie is the shallowest and warmest of the Great Lakes. Sustained changes in bio-optical and physical meteorological variables significantly impact lake ecosystems. So this study intends to explore cross-parameter linkages to understand the primary and secondary triggers. Again, this work is preliminary, and I expect to better explain things in a few months. Given the influence of lake depths on thermal stratification and bottom oxygen availability, it is required to stratify the lake by deep and shallow regimes. This was done using bathymetry and multivariate cluster analysis. This image shows the results of clustering to derive approximate thresholds of deep versus shallow waters. The 5 rows are for 5 lakes, and 5 columns are for 5 parameters: chlorophyll-a, KD490, LSWT or lake surface water temperature, wind speed, and precipitation. The thresholds we used are 54 meter, 21 meter, 38, 42, and finally 14 meter for Lake Erie. Yes. The data are from ESA or C3S, CCI, and NCEI, and the URLs are provided here for the 5 data sets. A shout out to CCI project for making these data available in an easy and usable interface. The efforts are very much appreciated, especially for the data intended for climate or homogenized rigorously for long time series applications. Now, very briefly about the concept of trend detection. As I mentioned previously, last October I presented the concept of trend detection with SST as an example for the open oceans. The YouTube link is there if you need a recap, so let's skip this discussion here. The papers are under review currently. Now let's get some idea about the time series and seasonalities of these parameters. Here on the left collage, time series of 5 parameters are shown for deep versus shallow parts of the lakes. The time series for 5 lakes are overplotted in each panel for a given parameter, which are identified in the y-axis levels here. This is a busy panel collage, but briefly we see strong seasonal patterns and large variations for most parameters. The panels of right show monthly average seasonal plots that highlights different months for high and low values. For example, chlorophyll-a for deeper parts of Lake Ontario, this line here, show peak in June, July, which is opposite for Lake Erie. I have not had the opportunity to explore this deeper or compare with in situ observations yet, but the plots provide some initial idea about the seasonality of these parameters in the Great Lakes. These are further analysis to understand seasonality. The top panel here shows percentage of explained variance on y-axis versus the principal components for 5 parameters and 5 lakes. For most cases, what we see is the first one or two PCs or principal components explain about 70% of variance or more. Likewise, the first EOF maps show the spatial variations. And the time series of PC1 or principal component 1 shows the dominant seasonal pattern. We'll skip the details today, but these are additional tests to get an idea about the seasonal patterns. Finally, the dominant periods are determined with Fourier transform and continuous wavelet transform and verified with these tests as well. The extracted periods are used in multiple seasonal trend using Loess or MS-STIL method to detect trend lines in these parameters for the 5 lakes separated by the shallow and deeper regimes. Okay, too much analysis so far. So finally, let's see some results of trend lines and trend rate maps. This shows the trend lines, multiple seasonality, and remaining noise after time series decomposition. The examples are for chlorophyll-a and lake surface water temperature for Lake Superior separated by deep and shallow parts for both the parameters. Other parameters and lakes have been analyzed, but I skipped them for now. The maps show spatial distribution of trend rates for chlorophyll and for lake surface water temperature for 1998 to 2023 end. A lot is going on here. For example, there may not be significant overall trend rate if we take the slopes, but looking at the time series of the trend, there are periods with increasing chlorophyll-a, whereas lake surface water temperature is more or less consistent. This is for Lake Superior. Recall it has minimum agricultural activity within Lake Superior watershed, but mining is commonplace. So some of these observations may be or may not be related to certain human activities or natural events that we need to investigate carefully sometime soon. To summarize the results that we have so far, this table shows the trend rate per year for the period of 1998 to 2023 separated by deep, given by D, and shallow parts of the 5 lakes. Recall the endpoints are important, and this is strictly for 1998 to 2023. Results may vary if we choose different start and end years. The trend rates are based on Mann-Kendall and Thiel-Sen methods at a significance level of 0.1, that is alpha is equal to 0.1. I didn't take 0.05. These data are very noisy. When the calculated p-value that's shown here is less than alpha, it indicates a statistically significant trend rate in the data. If p-value are more than alpha, there is not enough statistical evidence to conclude the presence of a trend. Those are marked in red font here. So the parameter lake combination in red indicate that there is not enough statistical evidence to infer that there is a trend in the data. The standard errors are also given by this plus minus sign here. As you see, they are calculated using the bootstrap approach rather than the usual analytical approach. This is because bootstrapping allows assessing the accuracy of the statistic without assuming the underlying distribution of the data, and lake variables show significant variability and seasonality. So this table basically summarizes what we see so far in the data and the 5 lakes, the trends in this data. Wrap it up here. In summary, in this preliminary effort, trend lines and trend rates for chlorophyll-a, KD 490, lake surface water temperature, wind speed and precipitation are derived using an established method for the 5 lakes, separated by shallow and deeper regimes of the lake waters. Trends that are statistically significant or insignificant have been identified. The work will be extended to include multivariate analysis to detect possible correlations among those trend lines and trend maps. So that's it for now. Thanks for your attention and cheers. Prasanjit signing off.